Okay, so for number one, we're trying to name this compound. The first thing we want to do whenever we're naming is count the longest carbon backbone that we can find. So let's start by doing that. We have 1, 2, 3, 4, 5 carbons. So it's 5. 5 is penta, so the answer should have penta in it somewhere. A has butanol, that's 4, so it's out. B has penta, so it may be it. C has propanol, that's 3, so it's out. And D has penta, so it's either B or D. And the way we know that is, let's look at both. What's the difference? They both have 3 pentanol, and the only difference lies in the numbering for the methyl group. So they're giving this OH the same number, which makes it makes sense because it's in the middle. If we number this, whichever way we number it, either making this carbon 1 or this carbon 1, which would give you 1, 2, 3, 4, 5, the OH ends up in the middle. So all you gotta do now is give this methyl group the lowest possible number, which is 2. So you would start counting from this way. So that would make the answer D. So it's D. Which compound or ion is aromatic? Okay, so we just gotta know the 4 rules that a compound needs to follow to be aromatic. First one is be cyclic. All are cyclic, so all are good. Now 4n plus 2. You need 4n plus 2 pi electrons. And since these rings are very small, I would say that n is going to be equal to 0 here. So 4 times 0 plus 2. That's just 2. We're looking for anything that's got 2 pi electrons. This A does have 2, but it's not a cyclic pi system. This is a ring, but you have an sp3 carbon right here. So the electrons are not going to be able to flow through it because of this sp3 carbon. That stops flow. That breaks one other rule for aromaticity, that is all carbons not sp3. So A is out because of the hybridization of this carbon. Let's see, B does have 2 pi electrons, and now they can go through because this carbon is sp2 due to the positive charge, so I would say it's B. In C, the electrons could flow, but now they're 4. We got 2 from the double bond plus 2 from this lone pair, so 4 does not follow the 4n plus 2 rule, so this is out. And D, there's a radical, so it doesn't even make sense to look at this, so let's just cross it out. Okay. Homostate of butadiene. Okay, so all we gotta do is draw butadiene. 4 carbons, 2 double bonds. What does this tell us? It tells us that there's 4 electrons in the pi system. 1, 2, these make the double bond. 3, 4, these make the other double bond. So let's draw the MO diagram. I'm not going to draw the complete thing because you're going to see that it's not really necessary. Because this thing has 4 carbons in its pi system, it should have 4 levels. But they're asking us about the HOMO, highest occupied molecular orbital. So which one's the HOMO? We have 4 pi electrons, as we just saw here. So we can fill out 1 electron, 2 electrons, 3, 4, and that's it. We don't even need to look at this. Level 1 will always have 0 nodes, so there are going to be no nodes here, and all of the lobes are going to be with the black part going up. And then level 2 is going to have 1 node. You always place them symmetrically, so it's going to go in the middle. You wouldn't place a node here or here in the beginning because it wouldn't give you a symmetrical placement. And now we fill them out. 1, 2, and then the spin changes, so it goes down. And that's what it should look like. Okay, let's look at the answers. Answer D would imply that there's a node here, a node here, and a node here, which doesn't make sense. This would be the last orbital. Answer C would mean that there's no nodes, and that's also wrong. Answer B has one node here, no nodes here, sorry, and one node here, which is wrong. And A does have one node here, so it's A. This process demonstrates. Okay, so let's look at the molecules. What's the difference? They both look like they have the same formula. One is a ketone, and the other one is an enol. En as in alkene, ol as in alcohol. So, keto to enol. This is tautomerism. I don't think I need to explain this one because it should be pretty intuitive by this point. But whenever you go from a keto to enol, it could also be, you could also see this in the form of an amine, so be careful with that. You could also see something like this going to something like this. Be careful with that. But yeah, this is tautomerism. What represents a reasonable reaction step? Okay, so for A, first of all, they're drawing arrows without bouncing them. So I don't know if this arrow goes to the C and then to the H, or to the O and then to the H. But based off of the product that they're getting here, I assume that they're using the carbon to grab the H. Yeah, it's doing this. First of all, this is, okay, I can tell that this is wrong because they gave oxygen a positive charge by breaking its octet. Since they had something like this, and they took electrons away from the O, and they broke its octet, I right away knew that that is wrong. You will never see oxygen with a positive charge because of breaking its octet. You only see it because of making three single bonds. Or like anything that just looks like this, or like this, but not by breaking the octet, so A is out. C. Okay, C looks good to me. It looks like it's just a normal acid-base reaction. Oxygen is grabbing a proton, so I'm gonna go with C. B. Okay, they're drawing an arrow that goes from an atom, which is this H, to another atom, and that is wrong. You always draw arrows that go from the electron pair to an atom. There are no electrons in H, even though there's a charge. Positive charge means no electrons, so B doesn't make sense. And D, I see. They're grabbing the proton with the OH, they're breaking that bond. But that also doesn't make sense because breaking this bond right here means that you're taking even more electrons from C, and we can see that C has a positive charge. So C should have a +2 charge, which does not make sense. So D is also wrong. Okay, so for number 6, this question is basically asking you, what is the mechanism of this reaction? Is it SN1? Is it SN2? Is it E1, E2? If it is SN1 or E1, it's going to be 2-step. And SN2 and E2 are 1-step. So which one is it? We have a primary alkyl halide, 1, 2, 3, 4 carbons, and a Cl reacting with nitrile. I'm going to draw it like this. So we have a primary unhindered electrophile and a primary unhindered strong nucleophile, which is our nitrile. So this should immediately hint you towards SN2. This is just going to come here and kick this out. And the product confirms that. This is what's going to happen. So you're only going to end up getting 1, 2, 3, 4 carbons, 5, This is what you get. And this is an SN2 reaction, which is one step. So now let's look at the diagrams. Which of these diagrams looks like a one-step reaction? Diagram A has an intermediate here. You go up to a transition state and then stop at an intermediate. That's one step. And then you go up to another transition state and go to the product. That's a second step. So A is two-step, which is not right. B is a one-step reaction. You go up to a transition state and go back down to the product. And it should be downhill, which makes sense. C, again, two-step reaction, same reason as A. Let's just cross it out, and same for D. These are two-step reactions. Okay, what would be the relative rate of hydrolysis of these compounds? Okay, so we are in, hydrolysis means reacting with water. So let's draw water. And water is also going to be our solvent in here. And we're not in very hot conditions. So we are in a polar protic solvent, which is water. There's also acetone, which is not polar protic, but since the water is polar protic, we can say that overall the conditions are going to be dictated by the water, because the acetone basically does nothing, but the water does something. So we just got to look at the water. Now, water is not a very strong reagent. It can't just attack anything in here unless we form a carbocation. Cl has to leave in all of these for something to happen. And this is going to be the limiting step of the reaction. And they're asking about the relative rates. So all this question boils down to is which one forms a carbocation faster. So let's look at that. These are all tertiary carbons, and the only difference is that one has a benzene, the other one has two benzenes, and the third one has no benzenes. So whenever a chlorine leaves, let's do the example for the first one, you would get a positive charge here. And this positive charge is going to be stabilized by the ring. You're going to get a positive charge here, and then a positive charge here and here. And hopefully you can see that the ring is going to stabilize the carbocation that is formed due to the Cl leaving. So 1 is definitely going to be much faster than 3 because 3 has no rings. There is nothing that can stabilize this carbocation once it forms. So 3 is going to be the slowest, 1 is going to be faster than 3, and then 2 is going to be the fastest because it's got 2 rings to help it stabilize the carbocation. So it should be 2, 1, 3, which is B. What is the relationship between these structures? Okay, so first thing we do here is look at the formula. Do they have the same formula? 1, 2, 3, 4 carbons. 1, 2, 3, 4. Yes. 1 double bond. 1 chlorine. Okay, so they do have the same formula. The only difference lies in where the atoms are connected, how they are connected. They just basically put this methyl in here, this chlorine in here. That's all they did. They switched them. And when you just connect things differently, that should hint you towards constitutional isomers. Different connectivity, same formula. These are not the same compound. These are not enantiomers. Enantiomer would mean mirror image. And these are not mirror images. Diastereomers, are we changing a chiral center or going from E to Z? So there are no chiral centers, and this molecule is Z, but this one on the right is neither. It's got 2 equal things on one side, so it's not even E or Z, so it doesn't make sense to go for D. Which carboxylic acid is the strongest acid? Okay, so they're all carboxylic acids. This is just asking you about the inductive effect. Whenever you have a very electronegative atom around something, that's going to lower the pKa by a bit. So which one has the most electronegative atoms close to the most acidic H, which we know is the carboxylic acid one? A has a chlorine, but it's sort of too far. It's 1, 2, 3, 4, 5 bonds away from the H, so I don't think it's A. B has the same chlorine, which doesn't do anything, or something, but very, very slight. And it now has this fluorine. This fluorine, this is, I believe, the closest you can get it, and it will affect this H. So it may be B. This is going to bring down the pKa by a bit. Okay, C, they took out this chlorine, and they instead put another F here. So C is for sure more acidic than B. So let's eliminate B now. D has a bromine, so not really. D has a bromine, so it doesn't make sense also. C has to be the most acidic one because it's got 2 fluorines close to that acidic H. So let's see. Okay. This one's just about doing RNS, so let's just do it. Okay. Let's number it. This is going to be carbon 1, 2, 3, and 4. This is going this way, so it's going to be R. One, two, three. This is S, so I think it's B, but let's do these ones. This one's not even chiral. It's got 2 things that are the same, so C doesn't make sense. And D is 1, 2, 3. The H is on a wedge, so it's going to be R, so it's not D. I did do these ones a bit too fast, but I don't really think I could explain this right now. But if you're feeling stuck on this, go back to the activity on chirality, try to understand the hand method, and if that doesn't work for you, there's a lot of things online that you could do, but just make sure to stick to something that you can understand. Okay, so for number 11, they're asking us, how does the potential energy of this molecule change as you rotate it about this bond that is depicted by the Newman projection? So, right now, this molecule is in its lowest potential energy conformation because you have the 2 biggest groups, the 2 ethyl groups, empty to each other. So if we were to draw a graph of the potential energy right now, we are starting at the bottom. Now, as we rotate it, I'm going to rotate it to this methyl group is in place of this H is in place of this methyl group, and this H is in place of this H. We're going from a staggered conformation to an eclipsed conformation, which is very high in potential energy. So the part that's in the the part that's in the back won't change. So this is going to stay the same. I'm just going to draw the ethyl group as ET. So this is what's in the back. And now I rotate it so that the ethyl group is right on top of this. So we have ET here, H here, and H here. This, anytime you have a eclipsed conformation, that is going to be a local maximum in the graph. So we're going to go to a very high point. And then, as we keep rotating it, now I'm going to rotate it so that it is in a staggered conformation, and the ethyl group is now where this H was, this H is where this H was, and this H is where the ethyl group was. This is going to look like this. Oh, and I should have drawn this like this, I'm sorry. This should look cleaner. Okay. So the second staggered conformation is going to look like this. And as we can see, the two biggest groups, the two ethyl groups, are not anti to each other anymore. So the graph is going to go down because it's not eclipsed anymore, but it's not going to go down by so much. It'll definitely be higher than when it started because it started anti and now it's gauche. So we're going to go down, but not to the bottom. Okay, let's keep going. Let's keep rotating this. Now, I'm going to rotate it so that the ethyl group is staggered with this, the H is staggered with this, and this H is staggered with this one. Okay? So hopefully you could see by now that that's going to be the highest ever point in the graph. This is going to look like these ones in the back, H, H, and the ethyl. And then we have ethyl here, H on top of this, and H on top of this. This is what it should look like. That's going to be the second eclipsed conformation, and it's going to be the absolute maximum. This is going to be the highest point in the graph. Now, if we keep rotating this so that the ethyl is now gauche again, this H is going to be right here, and this H is going to be right here on top. That would be the same conformation as this point in the graph, as the first local minimum. Because having the ethyl group here is the same as having it here. They're both gauche conformations, so they are the same. Because, not only because they're gauche, but also because there's two H's, so it doesn't really matter, and nothing matters except where the ethyl group is, because they're just H's. So the graph is going to go down to a local minimum. Now, C is out because it's proposing that all of the eclipsed conformations and the gauche conformations are, all the eclipsed and all the staggered conformations are the same in terms of energy. So C is wrong, it doesn't make sense. Same for B. Now we're just between A and D. And it's gotta be A, because D, they don't start, they start at the bottom, which would be this. But once they rotate it, you have to go up, because you start anti, but your next local minima, which would be your next staggered conformation, has to be gauche. And gauche is higher in potential energy than anti. So this does not make sense. This local minimum would have to be a bit up. It can't be at the same level as where you started, so D is wrong. It's gotta be A, because A is the only thing that looks like what I said. So it's gonna look like this. It's gotta be A. This question is on the harder end because you gotta sort of understand how every single conformation that the molecule can be in affects its potential energy. But hopefully you found these drawings helpful. Okay, number 12. You have a lactone and you're reacting it with base. So the only possible thing that we have seen is a lactone ring opening with base. So this OH attacks here, brings this up, and we have OH and O minus. Now, the negative charge on this oxygen is going to go back down and open the ring. This is on the one of the later activities. I think it's 25 or something like that, 24. But basically, you should be opening this ring. So you're going to get a carboxylic acid. Oh, let's number the carbons, by the way. Whenever you do ring openings and closures, it's super useful to number carbons. 4. And this is another carbon, but I'm also going to number it. So 1, 2, let's draw it. 1, 2, 3, 4, and 5 was an oxygen, so I'll just draw it too. Draw it like this. Okay. And then let's number it. 1, 2, 3, 4, 5. Number 1 had this oxygen, which became the double bond O, which I just drew. It also had this OH, so let me draw this OH. Number 2, 3, 4, and 5 look good. Okay, but there's an issue here. This looks to me like almost the right answer, but there's something else. This oxygen has a negative charge, and it will go after the H in here, because this H on the carboxylic acid is much more acidic than the H that could be here. This has a pKa of 5, and whenever this makes a bond, it's negative 16. So this will go after the hydrogen, and we get something that looks like D. This is exactly what D looks like. A and C wouldn't make sense because you have to open the ring. If you are reacting a lactone with a strong base, you have to open the ring. So A is out, C is out. And B, oh, they didn't form a carboxylic acid in B. There needs to be an OH here due to the mechanism that I just drew here, so B wouldn't make sense. It's gotta be D. Okay. So we're just reacting a double bond with BH, 3THF, H2O2, and AOH. Okay, I see. So this is going to be anti-Markovnikov addition of water, but we have to remember from ochem 1 that when we do this mechanism, the water is added, so you have 2 carbons, and to one you're going to add OH, and to the other one you're going to add H. The tricky part here is that the H and the OH get added on the same side in this mechanism. Specifically, the BH3THF adds the OH and the H on the same side. So we know that we're going to do the OH on the anti-Markovnikov carbon, which is this one. It's the least substituted one. So let's look for answers that have that. A doesn't even have the OH in there, so it's out. Also D, why would you form an epoxide? So we're just between B and C, and the only difference is the stereochemistry. So let's draw the ring. And let's draw OH and H on the same side. They have to be on the same side, which means that the methyl group is going to be on the opposite side. This would be the CH3. The only thing that looks like that to me is C. In C, they added the OH on a different side than the H. So B is wrong. Which of these are chiral? Okay. So let's just look for chiral centers. That's all they're asking for. This one, okay, this A is tricky because it does have chiral centers. 1, 2, sorry, no, not 2, that's not 2. 2, 3, 4. This is a chiral center, but the molecule has a plane of symmetry. Hopefully you can see that going from the line and up and the line and down is the same. This is symmetrical, so it is not chiral. So A is out because there's a meso compound. B, we have two things that are the same on this carbon, so this is not chiral. And same for the bottom one. It's also not chiral. C, we have two things that are the same and two things that are the same, so not chiral. D, oh, D totally looks chiral. 1, 2, 3, 4. This is the chiral center. And we have 1, 2, 3, 4 in here, also chiral center. So it's D. Okay, so question 15 is definitely on the harder end, and it's very similar to one you had on your midterm 2 from ochem 1 last year. It's asking you about tautomerization. They're saying that you have a ketone that reacts with base, but the base has deuterium. That's an important detail. And that when the reaction is over, I guess, you exchanged 5 of those H's for deuteriums, because you have 5 D's here. So you had 14 H's in the beginning, and now you still have, I guess, 14 H's, but 5 of them are D's. So where have you ever seen that before? I'm not gonna draw the complete thing out, but I will do an example one for y'all. So you have this ketone, and you reacted with base, OD minus. So this is going for this H, make a double bond in here, do this, and you're gonna get O minus, and your double bond here, and you still have an H in here. Now, this O grabs a proton from D to O. Let me redraw this. And you reform OD minus. OD. You have this. Now, what ends up happening here is that to go back from the enol to the keto, so you're in solution, so this thing is going back and forth between keto, enol. So once you're at the enol form, which I just showed you how to get here, you will go back to the keto by attacking with base, OD minus, and you push this here, and you end up getting double bond in here. And now here's the tricky part. You have a negative on this carbon. This is just a resonance structure of what I drew. You could have drawn it with a negative charge on the O also, which is valid. Like the charge is either going to be on this carbon. It's either going to be on this carbon or the O. So you have this, and now the tricky part is this. You are in D2O. So this negative charge is going to get a D instead of an H. And the net result of that is having a ketone which had one of its H's switched out for D's. And over time, this is going to happen to 5 H's. There are 5 H's that can undergo this change. I showed you how to do one of them, but you can do the other 4 and hopefully see how this 5 gets here. So that's one part of it. Let's look for molecules that could exchange 5 H's. This one has a ketone with 5 H's around it, so it could be A. C has a ketone with 5 H's around it, so it could be C. B has 3 plus 1, so it's got 4 H's. That's wrong. You need to exchange 5, not 4. D has 2 H's plus 1, so that's 3. It's also wrong. So now, what's the difference between A and C? Which is the answer? We gotta finish reading the question for that. The question says that the product is optically active, which means chiral. The product is chiral. So which one of these is chiral? Changing out the D's is not going to affect chirality. So let's not look at anything on this side for now. What is the difference between A and C? It is this methyl group. In A, the methyl group is here. And that difference makes this a chiral center. There is a chiral center here, and there are no chiral centers in A. So the answer is C, because it gets 5 H's and it has a chiral center. Okay. This is just another R and S question, so let's assign R and S. I will do the one on the left first. So 1, 2, 3. This is going clockwise, so it's R. So let's do that. This is R. And then this one is 1, 2, 3. Also going clockwise, so it's R. Both are R. So it could be A. This is S, doesn't make sense. B is out, C is out, and D is also out. The only one with both R's is A. Okay. Transition state. Okay, so for this one, we know that what's going to happen here is the nitrile attacks this carbon, breaks the carbonyl, and gets you to the product, which is drawn here. So you are in the process of making a single bond and in the process of breaking a double bond. So your answer should have dotted lines for this bond, for the CN bond, and one real line and one dotted line for the double bond though, because you're in the process of breaking it. Let me redraw this. So it would look like CH3, CH, this doesn't change, but we are in the process of making this bond, and we are in the process of breaking this bond. So what looks like that? A is not it. A is not a transition state. A is just the product drawn again. And between B, C, and D, the difference lies in the partial charges. Okay, so let's look at how we started. We are in the process of giving nitrile no charge. It started with a negative, but it ends with no charge. So in between having a charge and having no charge, you have a little charge, negative charge, right? So there should be a partial negative on the CN. So B is out. It doesn't make sense to have a partial positive on the CN. And now between C and D, you're in the process of giving O a negative charge, so it will also make sense to have a partial negative in here. So it's D. Oh, and this one isn't even a squiggly dotted bond, so it's also out. Okay. What is the product of this series of reactions? Okay, so you have a Claisen reagent here because it's an ester, and the base matches the ester, so that confirms what I was thinking about. It is a Claisen. So if you see this, and then you see that they're reacting it with a base that matches the ester, it's probably Clayson. You're probably trying to go after this H so that you can add the molecule to something else. And that something else in this case is number 2. So let's do this. The first thing that's going to happen is the base grabs the H and you form a carbon ion. You have a negative charge here. And then in the second step, you're going to react this with alkyl halide, CH2, sorry. This negative charge in the carbon ion is going to go after this carbon, just to normalize into reaction, and we get, oh, there we go, sorry. And we get 1, 2, 3, 4, double bond. 1, let's count the carbons. You always have to count your carbons. So you had 1, 2, 3 carbons. And the OCH3 is still here. So that is the product of these 2 steps. Now, what does acid, water, and heat do? The only thing H3O is going to do is it's going to change the ester so that it's now a carboxylic acid. So you're going to go from this to this. 1, 2, 3. And the reason why we do that is because we want this to leave. This is going to leave a CO2. This is part of the newer activities that we have been seeing. So that's what's going to happen in here. I redrew it like this so that I could do the CO2 forming step easily. This is what's going to happen. And then you get 1, 2, 3, 4, 5, and an OH in here. Notice how this is an enol. You still have to go back to the ketone because you are in an acid. That's going to be the catalyst that allows you to go from the enol to the ketone. So that's going to be the product. So A doesn't make sense. Why would you have 2 carbonyls? A is out. C is out for the same reason. You got 2 carbonyls. We're just in between B and D. D has a carboxylic acid, which doesn't make sense. B is exactly what we drew here. B is the same as this. Is it? Yes it is. Okay. Okay, so for 19, which intermediate is believed to be involved in this reaction? We are adding HBr to a double bond, anti-Markovnikov because we're using peroxides. I don't think we covered this a lot, but whenever you see peroxides, so like this, it usually means radicals. What ends up happening here is that you form 2 OR radicals, like this. The only exception to that I could think of is MCPBA. MCPBA is a peroxide and it doesn't form radicals. But besides that, you usually should form you should form radicals when in the presence of peroxides. So, this is not a carbocation, not a carbene, not a carbon ion. This is a radical reaction. And don't feel bad if you don't know this one. This is something that we didn't cover a lot. Okay. Which species is an intermediate in the base catalyzed formation of... Okay, I don't even think we need to pay attention to this because all of the answers are just propanol derivatives. So they're just asking you what happened to the propanol if you reacted with base. So let's draw propanol. 1, 2, 3 carbons and an H. And you're reacting it with a base. So the base grabs the most acidic H and gets you a negative charge in there. This is what you get. So what looks like this, that's A. B doesn't make sense because why would you get a positive charge? This would mean there's just no way you get this. B doesn't make sense. C also doesn't make sense. If you took a hydrogen away from this carbon, it would form a negative charge, not a positive charge. So it doesn't even make sense to get positives. And in D, they did take a hydrogen away from this carbon, so they had this, and they did the base do this. But this doesn't make sense because this H is way less acidic than this H. We gotta remember that the top hydrogen is resonance stabilized. This anion can do resonance with the oxygen, while if you had a negative charge here in the bottom, you couldn't do that. So that's why it doesn't make sense to grab that bottom H. What is the order of reactivity of these compounds with methylamine? Okay. We have just a bunch of carbonyls. I'll redraw them. OCH3. And then NH2. And then an acid chloride. So, how are these different? We know that methylamine has to come and attack the carbonyl. So, they're just asking you which carbonyl is the most activated, which one has the most electrophilic character. So, chlorine is withdrawing electrons away from this carbonyl. So I would say that this carbon is activated, and oxygen and nitrogen donate electrons. They don't withdraw them. I mean, they do a little bit of both, but they donate much more than they withdraw. So N2 is overall gonna donate, and NO is also gonna donate. So the acid chloride is going to be the most reactive one. So it should be 3, which should be the first one. So A is out and B is out, just between C and D. So the way we decide between 1 and 2 is the amine is a much stronger donating group than the O. This is something that you should know from the EAS activity. If you're unsure about which groups donate more or less than others, go back to that activity. But you should know that nitrogen is the strongest donating group, so that's going to make 3 the slowest. Sorry, 2 the slowest. So C is wrong. The best reagent to accomplish... Okay, we're just making an epoxide. And the only way we know to do that is MCPBA. Oh, this is MCPBA. So meta, chloro, peroxy, benzoic acid. You gotta know how to name it, so there it is. Water wouldn't make sense. Water and acid would just either give you OH in here, or yeah, that's what it's gonna do. So water doesn't make sense. Acid doesn't make sense. It'll probably eliminate this OH. and ozone doesn't make sense. We would probably cleave this bond if we added ozone and something else. Okay. Okay, this is an EAS question. You start with toluene and you're gonna sulfonate it. So you react it essentially with SO3. So we know that the methyl group in toluene is an ortho and para director. So whatever we attach has to go to the ortho or para carbons. So let's look at the answer choices. A is adding the SO3 to the same carbon as the methyl, so it doesn't make sense. B is adding it para, so it could be. C is adding it meta, so it doesn't make sense. And D is adding it also para. So the difference lies in the intermediates. Where is the positive charge gonna go when you add it? So let's draw the first step of the mechanism. If we wanna add this para, we have to break this double bond and attack the sulfur. So you're gonna get something like this, positive in here, and SO3 minus in here. So you get a positive charge on the carbon that is meta to the methyl, which is B. This is B. It cannot be D because D is proposing a positive charge on the carbon ortho to the methyl group. And you can't do that. If you try to do the resonance structure for this, you can only get the positive charge on this carbon. And then if you move these ones, you're gonna get it on this carbon. So you will never get it on the one that's ortho. So that's why D is wrong. Okay, so 24 is asking us to say which synthesis is the right one. In these questions, we have to do it. There's almost never shortcuts. There is one in here, though. You can immediately know that A is wrong because they're proposing Friedel-Crafts alkylation, which is going to add a methyl here, but then the ring is more activated, right? So it's going to want to add another one. And then it's more activated, so it wants another one, and another one, and another one. And you're just never going to stop. And you're going to get this product. So A is wrong. Whenever you see alkylation being proposed as one of the first steps, it is probably wrong because you can't control how far it goes. So A is wrong. B, okay, let's draw this out. So B, they do bromination. So I'll draw it here, Br. And then that's one. And then in step 2, they do acylation. So this looks right to me. What they're doing is they have this Br here, which now directs ortho and para. We're gonna add para. We have 1, 2, 3. That's what you get from that. And then, okay, what is this? This is ethylene glycol. This makes sense because it looks like they're trying to protect the ketone from whatever's going to happen in the next step. So, if you protect the ketone with ethylene glycol, you will get this. This is what you get. That's step 3. And then in step 4, you're making a Grignard reagent. You have a bromine on your ring and react it with Mg. So all that's going to happen is that you basically get a negative charge on this part of the ring. which if you didn't do the protection of the ketone, this negative charge would have messed up the ketone. So that's why you protect it. So this is all making sense. I really think this is the right answer. Then B, CH, okay, so they react this with formaldehyde. I'll just draw it here, I guess. This is going to attack this carbonyl, and you're going to get product 5, which is just 1, and then OH, and then you do this. Okay, that is step 5. And then in step 6, you just add acid and water to deprotect the ketone. You want to go back to that ketone that you had initially. This is what you should get. And that looks to me, that is a product. So B looks right, I think it's B. Let's still do the other ones though. So for C, you brominate first. So you get a bromine in here. Then you make that into a green yard. Okay. So you get a negative, basically. And then you react that with an epoxide. Okay, that's just wrong. Because when you react that with an epoxide, you're going to go and attack here, break this here. That's going to give you 2 carbons, and then OH. The answer has 1 carbon, and then OH. This is 2 carbons, so this is wrong. So C is out. And then for D, let's see what they did for D. They do acylation first. So you have your ring, you acylate it, and then you brominate. If you brominate this, it'll brominate on the meta positions because the ring is now deactivated. So you get either this or this. The BR can only be on these 2 spots, which does not make sense because the products are, they have para substitution, so D is wrong because of that. Okay, what is the major product of this reaction? You're reacting a triple bond, an alkyne with acid and water. We know that when that happens, when you have something like this, and you react it with acid and water, you get a ketone. Always. So the answer should at least not have the triple bond because we know that needs to react with the acid. So A, they still have the triple bond, so it's not right. B, they did react the triple bond, but this is what would happen if you do it on base, not acid. Because base, I'm gonna redraw this with OH minus H2O. This is gonna give you an aldehyde. This is part of your synthetic transformations index, so if you're unsure of what's going on here, just go take a look at that. I think that's from ochem 1. So B is wrong because of that. And then, also, I'm not sure if we covered this mechanism extensively, but you should definitely be able to work your way through it now. So try to do that. I think it's a good exercise for this upcoming final. Okay, answer C has a double bond. You reduced the thing somehow, which doesn't make sense. you need to either add water somewhere or get rid of the triple bond, so this doesn't make sense. And also they got rid of the OH. So no, it's not C. Now D. Okay, D makes sense because what happened here is that I'll redraw the thing. So you had your ring, you have OH in here, and then we know that you formed this ketone, but now you are still in acid and water. So this OH is gonna grab a proton. It's gonna become H2O plus. You still have your, oh wait, why did I even draw it here? What am I doing? Sorry, it goes here. And then you draw your ketone here. The water is going to get eliminated, and you're going to get this double bond that's in the answer here. The reason why is because, well, acid and water can promote elimination sometimes, but it's very favorable in this case because once you get rid of this H and form this double bond, kick the water out, you will get an alpha beta unsaturated compound. This is very favorable. Sure, this is not the best drawing. This is very favorable because of that conjugation that we're getting now between this double bond and this double bond. So the fact that you have a ketone in here promotes the formation of this double bond. So D is what makes sense here. What is the order of reactivity of these benzenes towards EAS? Okay, so which one's more activated, which one's more deactivated? This group, donating, so I'll put a little green arrow going up. This is also donating, so up. This is very fast. Now, we have also something that donates here, methyl group donates, and this is a very strong withdrawing group, so that's gonna make it go down. Let's look at this one. Two relatively strong donating groups, so two up arrows. So we know for sure that 2 has to be the slowest, so let's just look for an option that has 2 as being the slowest. That is D right away. None of these make sense because none of them have 2 in the end. So it's got to be D. All right, for 27, they're asking us which of these CO2s can leave. And this is kind of a tricky question, so I think it's better if we redraw it. Let's draw the carbon backbone. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. We have a double bond in here, CO2 in here. And then another CO2 in here, and an OH in here. And this is also CO2. So for decarboxylation to happen, you need to break the bond that connects the CO2 to the whole thing. And that bond, for the case of this, that bond for the case of this CO2 is going to be this bond. So when we break that bond, let's say a base comes in, grabs this H, makes the CO2 bond, you have to break this bond. But where are you going to move it to? You can't do anything about this bond. The only way you can move it is to go here, but it doesn't make sense. You would now have 5 bonds on this carbon. So you can't really get rid of that. And I guess we can look at the original CO2 leaving mechanism that we saw in the activity, which is this one. You're used to seeing it like this. Notice how this gets the H, then this goes here, and the bond that you're trying to break is this one. And it's totally okay to break it because you push this around. This carbon is never going to have 5 bonds because even though you made this new pink one, you broke this green one. And you can only do that because you have a carbonyl, you have a double bond in here, which you don't in here. So this cannot leave a CO2, and that is CO2 number 3. So answers C and D are both out. Okay, so we're just in between 1 and 2 right now. Hopefully you could see that the place where this is going to happen is CO2 number 1. And let me redraw this. So you have a base. You could either do it with a base or this carbonyl grabbing it. Whatever is fine. But let's actually do it with the carbonyl this time, because I did it with a base in this example. So the carbonyl grabs this H. Now you form the CO2 double bond. And now you can definitely push this around. You can push it this way and break this bond. And everything's okay. So you can definitely lose 1. So the answer is 1. Okay, hydrolysis means reacting with water. So we're going to add water and some acid catalyst. So what happens here? This looks to me like a protecting group. So when we want to protect something, we remove water. We start at some molecule and then we react with acid and remove water. So we want to go back. We identify this as a protecting group, so this is going to leave. And what would you have before this? This is definitely a ketone. This was a ketone before protection. So X here is just cyclohexanone. And that looks to me like it's definitely not B or C because you needed a ketone. You can't protect an alcohol like this. The only difference lies in these two things. They have ethylene glycol here, and they have just ethanol in here. Ethanol is not used to protect things. You know, I mean, this OH can definitely attach to this carbon, but you would need another OH that also attaches so that you can form this little nice protecting ring. So A is wrong. You need ethylene glycol specifically, or something with 2 OHs that you can attach. So it's D. Which one is not an example of EAS? Okay. First one is Friedel-Crafts alkylation, that is EAS, so it's not A. Oh, it's B. We know that you can brominate a ring through EAS, but these reagents are not EAS reagents. This is just going to make a bromine radical. And you don't do EAS through radicals like that. You need a bromine with a positive charge so that the ring can go and attack it, but not a radical. So this is not an EAS reaction. It's B. Let's still do C and D though. This is sulfonation of benzene, and these are the correct reagents, so this is fine. And D, also chlorination, these are the reagents, so it's fine. So if it was Br2, FeBr3, then this would be EAS, but this is not EAS. Okay, so 30 to me looks like an alkyl reaction. You have an aldehyde, which is 3 carbons long, and you react it with a base. And as we saw in one of the previous questions, the base has to take this H. It doesn't make sense to take this one or the ones in here. They're not really acidic. So once the base comes and takes this away and gives you the negative charge on this carbon, you will get something like this. Now, in an alkyl reaction, this is going to be your nucleophile, and the electrophile is another one of these, but in its protonated form. So this negative charge is simply going to attack the carbonyl. And you get 1, 2, 3 carbons. It's good to number them because you might lose a carbon or gain a carbon whenever you're drawing, so number them so that doesn't happen. 1, 2, 3, 4, 5, 6. So this is 1, 2, 3, and we know that 2 bonds to 4, so 4, 5, 6, 4, 5, 6, and 4 had a double bond O. It now has O minus. Okay, that was the first step of the reaction. This was the part where you add the base and water, but now you add acid and water. So what this is going to promote is, again, as we saw in one of the previous questions in this test, so the O is going to get protonated, and I'm not going to redraw the whole thing, but I'll just put the H here now. And then it'll get another H because we're in a strong acid. So you're going to get H2O plus. And now there is a hydrogen here, which you can eliminate. And that is very favorable because once you do that, you again form an alpha beta unsaturated compound. 1, 2, 3, 4, 5, 6 carbons. And you just make this double bonded here. This should be your product. So what looks like this? It's a bit tricky, but oh, this is literally A. They're the same thing. B didn't eliminate the oxygen, so B is wrong. They also put it in some other carbon. C has the ketone. C has a ketone and we have an aldehyde. This is an aldehyde. So C doesn't make sense because of that. And D also has a ketone, so it doesn't make sense. And they also left the OH. So it's A. Which reagent could accomplish this conversion? Okay, you're going from an alcohol to an aldehyde. So that's an oxidation reaction. Which of these are oxidizing reagents? KMNO4, Na2CrO7. These are all strong. I believe that these would all take you, well, not this one. OSO4 is gonna add OHs to both carbons in this double bond, and that's not what you're trying to do. So it's not OSO4. KMNO4 and NaCr2O7 will give you a carboxylic acid. They're not gonna stop at the aldehyde. They're way too strong for this, and will give you a carboxylic acid. And that's not what you want. So B and C are wrong. And D is PCC, and this is pyridine. It's an ion because of this H, so it's pyridinium chlorochromate, PCC. So it's D. What's the product of this reaction? Okay, this may seem very intimidating, but there's really only one thing that could happen here. You have a strong base and you have this molecule. Where can the base go? The base is definitely not going to go for the O, not going to go for this carbon, not going to go for this H, not going to go for this O, or these H's. None of these would make sense. The only thing that makes sense is to attack the carbonyl. So we get this. Now, what can happen here? You reform the double bond, but you have to kick something out. Are we kicking the benzene out? No, that's not a good leaving group. Because breaking this bond would be about 50 pK units of energy, which we know is not really favorable in this case. While kicking these out would make sense, because making this bond back again is about minus 16, and breaking this is about plus 16. So these two are the only options that make sense in terms of pKa. Now, they both can happen, but if the bottom one leaves, you just go back to where you started. If this leaves and you reform the double bond, you just go back here, which wouldn't make sense. Because it does make sense because it does happen, but you gotta remember that you're in excess of this. So over time, this will happen much more than kicking the ethanol back out. So your product is going to be, over time, it's going to be this. Because you have much more of this base. You're in excess. It's really important for you to understand that concept of what excess does to a reaction. So that's going to be D. In C, they're adding, they made an oxygen-carbon bond to this. C just doesn't make sense. B, they separated the ring and what looks like an ester to me. So no, B doesn't make sense. And A, no, A doesn't make sense also. This charge has to go back down and kick either this or this out. So A is wrong. How could this be affected? Okay, it's just a reduction. You go from a double bond to a single bond. But it is a selective reduction because you have another double bond in here, and you could also reduce it, but you didn't. So you have to react this with something strong enough as to reduce the bottom one, but weak enough as to not mess with the top one. So this is oxidizing, so it's out. We're not oxidizing, we're reducing. NaBH4 makes sense. It could be this. H2, 100. No, this doesn't make sense. Lithium aluminum hydrate. Yes, it's either B or D. But the thing is, if you do lithium aluminum hydrate, you will also reduce the top one. Lithium aluminum hydrate is very strong. much stronger than NaBH4. So lithium essentially reacts with everything you put in front of it. So it's not lithium. NaBH4 is the only one that will selectively deliver this H and not this H to the top one. All right, so question 34. We have this compound reacting it with bromine and light. So we're going to brominate. Let's just look at the answer choices for this one. Would it make sense to brominate this carbon? Not really, because bromination prefers tertiary carbons over secondary over primary. So if you can brominate a tertiary, you will do it. If you can't, then you do a secondary. And if you can't, then you do primary. But here, you definitely can brominate secondaries over the primary. So it wouldn't make sense to brominate this one on the primary one. So it's not A. And in case y'all are wondering, this is tertiary, why not brominate it? You can't brominate it because if you do it, you would break the aromaticity of benzene. Benzene rings don't react unless it's EAS or NAS. Okay. And B is just what I said. You can't brominate benzene. C makes sense. D also makes sense, but the reason why it's C and not D is because you need to look at the intermediates. Assuming that you brominate this one, the intermediate of the reaction is going to look like this. You will get a radical on this carbon or this carbon if you choose to brominate this one. But this one on the right is not stabilized by resonance, whereas this one on the left is stabilized. It is benzylic. It is right next to the benzene ring, so it can definitely do some resonance. And you will get radicals distributed all around the ring, which you don't get with this carbon. You can't move that around. So that's why, because C has a more stable intermediate, C is the answer. This reaction will yield. Okay, you have an epoxide. C6H6 is benzene. There's one less H because they made it into a Grignard reagent. So we just gotta recognize that. This just looks like this, basically. And they're reacting it with ether. Sorry, ether is a solvent. They're reacting it with an epoxide. This is just the basic opening of an epoxide, because this is a base and this is an epoxide. And you will get this O minus, and then you neutralize with acid, so this minus will just become OH. So this is your end product. They're not drawing it here, so we have to figure out what the formula is. So we got 1, 2, 3, 4, 5, 6, 7, 8 carbons. C8. How many H's? 1, 2, 3, 4, 5, 6, 7, 8, 9. 10 plus there's one in here, so C8H10. And 1 oxygen. So C8H10O. What is C8H10O? It is C. It's C. This is the benzene, and this is attaching it to essentially this ethanol. So it's C, and it's the same formula that I just drew. And these wouldn't make sense because this is an ether, this is saying that you have this, which doesn't make sense. This is saying that the ring opened the other way, essentially. That even though you attack it with the ring this way, we know that it has to open this way, but they're opening it this way, which doesn't make sense. So B is wrong because of that. And D is just giving you two different products with, and this wouldn't make sense. Okay, 36. Okay, how do you go from a double bond to a single bond without messing up the carbonyl? Water and acid is not going to do it. Lithium aluminum, it is a reducing agent, but it won't reduce this, and it will mess up with the carbonyl. So it's not B. It's definitely C. H2 and palladium is the exact reagent that reduces triple bonds all the way to single bonds, or double bonds all the way to single bonds. But it won't mess up with a carbonyl. NABH4, not really. It would also go for the carbonyl. So this is also wrong. Okay. In which reaction are we oxidizing something? So option A looks to me just like SN2. This is just going to go and attack here, break this bond, and you form this. So this is just SN2. No oxidation or reduction. B is a reduction. It's not an oxidation. You're adding H2, which is H minus, and H plus. You're adding 2 electrons, so you're reducing. C. What changes here? Okay, you have a carboxylic acid and you change it into an ester. This is not an oxidation reaction, this is an esterification reaction. You turn a carboxylic acid into an ester. So it's not C. D is definitely an oxidation reaction. This is an oxidizing reagent. You go from a single bond on OH to a double bond, so yes, this makes sense. Okay, question 38 is just another EAS question. They're asking us which of these carbons is the better site for EAS to happen. So let's analyze them. This ring on the left is deactivated by this group, and it's also activated by this R group. Because even though this is this on the right, even though this is a ring, it still counts as an R group. In here, you're activating it towards the ortho and para positions. So this one on the left is deactivated and activated at the same time. And the one on the right is also activated by this, so that arrow makes sense. And then also activated by this methyl, so 2 up arrows. So since the ring on the right is much more activated than the one on the left, we can right away get rid of 1 and 2. And now it just comes down to 3 and 4. What's the difference between 3 and 4? I think it's just sterics. Because this methyl activates this position and this position. And this methyl, well not methyl, but R group, activates also this and this. And the ortho positions are also activated, but they're already taken, so it doesn't even matter. So it just comes down to sterics. I think it's easier for something to get in here than something to get in here, because number 3 would be closer to the ring. So whenever something's on its way, it may bump into the ring and just not make its way to number 3. Whereas number 4, there's definitely less things blocking it. So it could make its way into 4. So I think it's 4. The imidazole ring system, which contains 2 nitrogens, is found in the amino acid histidine. Which statement is true regarding the basicity of the 2 ring nitrogens? Okay. This is about aromaticity. We should be able to recognize that this is an aromatic molecule because it's cyclic, it's got 4n plus 2 electrons, it's got 6 in this case, it's got 1 in here, 1 in here, 1 in here, 1 in here, and 2 from the lone pair in this nitrogen. This lone pair is unhybridized. It's in a p orbital, and that allows it to participate in the pi system of the ring and make it aromatic. So that's where the molecule is aromatic. And it's all not sp3, and also I'm missing something. Oh, planar. So this is aromatic. Now, what's the difference between these 2 nitrogens? They're asking you which one is the stronger base. Yes, they are asking you that. For something to be a base, it needs to donate its lone pair and attack something. So let's think about the differences between the lone pairs in these 2 nitrogens. This nitrogen has 1 lone pair in here. This nitrogen has 1 lone pair in here. So nitrogen 1 has its lone pair in a hybridized orbital because it already has 1 of its electrons in the pi system of the ring. 1 of its electrons is already in a p orbital, making this double bond. So this lone pair is not participating in aromaticity. Now let's look at this lone pair. This is definitely participating in aromaticity. This is in a p orbital, so that it gives the ring the 6 electrons that it needs. Because 1, 2, 3, 4 plus 2, 6. So if this nitrogen number 2 were to act as a base and donate its lone pair, this would mean that the molecule is no longer aromatic because there's no lone pair in a p orbital anymore. Whereas if you use number 1 as a base, nothing happens. It's totally okay because this was never participating in aromaticity. So by that logic, 1 is definitely more basic than 2. So that should be the answer. Yes, it's B. Both are strongly basic since the ring is aromatic. No, not really, because the lone pairs are being used differently. 1 is being used for aromaticity, the other one isn't. So it's not A. It's not C because, I said it's B. And then D, neither would be considered basic. Yes, one of them would be considered basic for the same reason I mentioned in A. Okay. This is a hard question, but I hope that I could make sense out of it in your minds. Okay, so 4D. These reagents react with ketones by mechanisms that can be considered nucleophilic addition reactions. Right. Nucleophilic addition, ketone. You have a nucleophile, so all of these could be nucleophiles. And this carbon is the electrophile, the carbonyl carbon. So, which one of these is reversible? Okay, this is simpler than it looks. So, you could sort of pattern recognize to be able to answer this question, which I don't recommend, but you'll get away with it on this question. So, lithium aluminum hydrate basically just delivers an H minus. CH3-MgBr delivers a CH3 minus. CH3, okay, methanol and acid doesn't deliver any negative charge. You know, the acid is gonna do something to the ketone, and then this comes in. Like, the ketone will grab this, and then this happens. And now it's activated, and this can come in here. And D is also essentially a carbon ion. So you can notice that A, B, and D are all carbon ions. And when they react, if we draw the energy diagram, it's really, really downhill. Whereas C, which is just an acid-base reaction, it's not really that downhill, especially because we have a very strong acid. So it'll look something like this, maybe. It's not a big change. It's definitely harder to go back up in here than it is to go back up in here. It's too tiny. So let's see. These are all downhill, and this is also sort of downhill, but not a lot. Okay. How could this conversion be carried out? So you wanna, okay, what they're doing here is they're just adding one more carbon. How do you add one carbon? That's all it's asking for. This is the same as this. So let's do it. These ones, we have to do them. So HBr, okay, HBr would just react with the OH. It's gonna make it a positively charged oxygen. And usually you should see something like this happening. You should have OH2 plus leaving and forming a carbocation. But you can't really do that here because this is a primary carbon. If this was maybe a secondary carbon or tertiary, I could say maybe this happens. But right here, the only thing that's gonna happen is just this, acid base, because the OH cannot leave as it is right now. And then you have Mg ether. This is trying to make a Grignard reagent, but you can't make a Grignard out of this. So no, this doesn't work. A is wrong. You need to have an alkyl halide to make a Grignard reagent. This with Mg and ether, then definitely, but not this. Okay. Let's keep going. So B, pyridine and CrO3. Okay. This looks to me like oxidation. So you're starting with this, and after step 1, you will get this. Pyridinium chromate. This is what this is, I believe. And yes, it will oxidize this into an aldehyde. Now, you're gonna react it with a Grignard reagent, okay. And these can react with aldehyde, so this is correct. So step 2 is proposing that you have a CH3 minus, essentially, because this is what this is. It gives this C almost a negative charge, so it's okay to draw it like this. This is going to go and attack this carbonyl, move this up, and you will get extra carbon. You just add a carbon, which is what we were trying to do. So this, I'm liking this. And you got a negative charge in there. And now the last step is just neutralizing it with acid. So I'm not going to draw this. I'll just draw OH. 2 and 3. And this is what you want. So it's B. C is wrong because if you react this with a Grignard, it will just do acid base. Doesn't make sense. Why would you want to do that? And then D makes even less sense. We saw the same thing in here in A. You can't make a Grignard out of an alcohol, so it's wrong. Okay, so this is the last page. We're almost done. This is an NMR question, and honestly, if I was taking this, like in a real exam, I would leave these for last. NMR is what I hate the most, and unless you're really good at it, I will leave this for last because this is very time consuming. But anyways, let's do this. So the fastest way to do this, look for how many peaks are in the graph. 1, 2, 3, 4. Peak clusters, not peaks, because there are 2 peaks in here, but this is 1 peak cluster, sorry. I meant peak clusters. So there are 4 peak clusters. That means that there are 4 distinct hydrogens in whatever molecule that we're analyzing. This peak doesn't count because it's the reference peak of tetramethylsilane. It's just something that they use to serve up as a reference peak. So we ignore that. Let's look at these molecules. Which one has 4 distinct H's? That one's going to be the answer. So this one has, these two are the same because of symmetry along this axis. So that's one type of H. And then same for these 2 H's here. That's 2. But then this is 3, 4, 5. That's 5 H's. So this is wrong. It's got more than what we need. Let's look at this one. There is no symmetry along this axis, so all of these H's are going to be different. So 1, 2, 3, 4, 5, 6. That's more than 4, so it's not what we need. Let's look at C. We got 1, 2, 3, 4, 5. There is symmetry, so this would be 3 and 4. These are also equivalent H's. Okay. So it's got 5, so it's not the right answer. And this one has 1, 2, 3, 4, 5. Okay, wait, something's off here. It's definitely, oh, I see what's going on. Okay, it's definitely not A or B, but even though there is 4 peaks in this graph, we gotta look at this piece of information. This is telling us something. This is an H NMR, which means that D's are not gonna show. H and D are different when it comes to NMR. So one of the peaks is being masked because it was exchanged with D2O. So some atom in one of these 2 molecules had its H's switched out for D's. And which H's are the most likely to do that? Those are the most acidic H's. And it will be for sure this one or this one. So let's switch that for a D. And let's switch this for a D. This means that there's no peaks being produced due to these H's because they're D's. They're being switched out by D's because I believe there was D2O in the solution or something. So let's recount the peaks. 1, 2, 3, 4. 1, 2, 3, 4. This makes sense now. It's either C or D. We just gotta look at the splitting now. And in case y'all are wondering why these H's are not being switched out by D's, it's because they're not acidic. The pKa for losing those is close to 50 for all of them, I would say. So it wouldn't make sense. Whereas this one in here, I think it's about 5. It is very low. I don't know the exact number. Okay. So, what is the difference? Let's analyze each peak individually. Let's just cross this out because it doesn't matter. Okay. So these H's, we said they were equivalent, and they're both going to be split once. This H splits this H, and this H splits this H. So we should be seeing, due to H number 1, a peak that is split once. It should look like this. And same for H number 2. This is going to be split once because of this H. It's 1, 2, 3 bonds away, so it splits it. So let's look for these peaks. They are these peaks. Here are your doublets. But this doesn't really give us a lot of info because this molecule here in the bottom also is going to have the same 2 doublets. So it's going to come down to whatever is in here. Oh, I know what it is. So this H isn't going to be split by anything. There are no H's 3 bonds away from it. So you should see a singlet due to this. And there's no singlets in here. This is a reference one, so we ignore it. This is a quartet. This is a triplet. No singlets. So it's definitely not C. Now, let's look at this. This H right here, well, these 2 H's are going to be split 3 times. So you had a graph that would look like this. You cut it 3 times. You're going to get 1, 2, 3, 4 peaks. Those are those H's. And then for this last carbon, the H's are going to be split twice. So you had your peak, you cut it 2 times, and it's going to become 1, 2, 3. Looks like that. So quartet, triplet, quartet, triplet. So it's definitely D. This was a very tricky question because of that D2O exchange thing. So make sure to look at every single piece of information that they're giving you in these NMR problems. Because if this was an H NMR, I mean, it is an H NMR, but if the H's in the nitrogen weren't substituted with D's, there would be a peak. It's just because they were exchanged with D's that they don't show up. Okay, last 2 questions. An aromatic compound undergoes free radical bromination. Okay. You're trying to know what's the original compound. You went from C9H12 to C9H11Br, so you brominated, and then you went from that to C9H10. So on net, this looks to me like an elimination reaction because you lost 2 H's. You start with the C9H12, you end with the C9H10. So what's going to happen here is that you have something, you brominate that something, you lost 1 H there, and then you eliminate. You're going to form a double bond. And this is not the molecule, right? But just to give you an example of what the mechanism would look like. So, the question is just asking you which molecule can I brominate and then eliminate. You definitely, I mean, you could brominate all of these. But you can't do elimination in B and D. Because for B, if you get a bromine attached here, you need a hydrogen beta to it so that you can do elimination. So you would need a hydrogen here, but there are no H's there. There's no H that you can eliminate, nor here, nor here. So you can't do this. You can't, like you could maybe add the Br, but not eliminate it. Same for D. Now for A and C, the only difference lies in the fact that C has a tertiary carbon and A has a secondary carbon. A has no tertiaries. And remember that bromination prefers tertiary over secondary over primary. So this reaction would give a higher yield if you do it on C, because C does have a tertiary carbon, whereas A doesn't. So what's going to happen is you brominate here, and then you eliminate one of these H's with a base. And this leaves. So it's C. Okay, so for this last one, it just comes down to knowing your pKa's. Identify which functional groups are here. We have an alcohol, we have a carboxylic acid, and we have an amine. The pKa for the amine being deprotonated in this form is 9. If we want to lose one of these H's, we need at least 9 pKa units of energy. The pKa for this thing is 5 in its acid form, right? Like you need 5 pKa units of energy in some base to be able to break this OH bond. And for the water on the left here, it is 16. But I think it's more useful if we look at this from the perspective of H3O+. So the pKa for this, we know it's 0. It's a very strong acid. So if pH is greater than pKa, then you get conjugate base. If pH is lower than pKa, then you get conjugate acid. So if the pKa for this being protonated is 0 and we are above it, we will have the conjugate base of H3O. So this will stay as it is. This is okay. Now for the amine, it is 9 and we are at pH 1. So we will stay protonated. If you want to deprotonate the amine, you have to go above pH 9. So this stays as it is. And for the carboxylic acid, if you are, so we said that the pKa was 5. So if you are below that, you will be in the acid form. We are at pH 1, so we will have an H here. You only get this form if you're above pH 5. So the final molecule should look like HO, CH2, CH, and H3 plus, and COH. So it's not A, it's not B, not C, it's D. Okay, I hope you found that helpful, and please let me know if you have any questions. I'll be on the lookout for that in Ed discussion.